working with concentration. Most of the time in here when we're dealing with concentration, we're going to be working with molarity. So what we're going to do is determine the molarity for each of these solutions. So we're going to start with 0.444 moles of our solute. In this case is cobalt 2 chloride, and that's going to be in a solution volume of 0.654 liters. Now molarity, capital M molarity, is moles of solute over liters of solution. So because we are given moles and liters here, it's a quick calculation to find that this is 0.679 capital M molarity. Double check your sig figs. You had 3 sig figs in both of these quantities, 3 sig figs here. Number 2, 98.0 grams of phosphoric acid in 1 liter of solution. 99% of the time in here, when you see grams, you're going to be converting it to moles. So we need the molar mass of phosphoric acid. Now, P, these are the values I'm going to be using. So P is 30.97 grams per mole. H is 1.01. And O, I'm just going to be using 16.00. So I need 16 times 4 because there are 4 atoms of oxygen in phosphoric acid, plus 1 phosphorus, 30.97, plus 3 hydrogen. And I get 98 even, 98.00 grams per mole. And that's phosphoric acid. I can't seem to write phosphoric acid, but there it is. So we have 1.00 moles of phosphoric acid. So to find the molarity, capital M molarity, it's 1.00 moles over 1.00 liters. I have 1.00 capital M molar, or molarity, of H3PO4. Number 3, a 0.2074 grams of calcium hydroxide in 40 milliliters of solution. Again, 99% of the time you see grams, you need to convert that into moles. So we need to find the molar mass of calcium hydroxide. So for calcium, I'm going to use 40.08. Oxygen is still 16, hydrogen is still 2. Now this time we have our 1 calcium, and we have a total of 2 oxygen and 2 hydrogen. So I get 74.10 grams of calcium hydroxide for every 1 mole of calcium hydroxide. Now again, I'm determining the moles so that I can find the molarity. So I'm going to take my 0.2074 grams divided by 74.1, and I get 2.79. I'm going to give you several digits, but you're just going to leave this in your calculator. And this is moles of calcium hydroxide. Again, leave it in your calculator and then divide these moles by the solution volume in liters. So if you can't do this conversion in your head, that's okay. You're just moving this decimal point over 3 spaces. So it's 0.04000. So divide your moles by 0.04, and that's liters, to get a molarity of 0.06. I get 997 and then a 3. Now I'm going to double check my sig figs. I had 4 significant figures in the mass and 4 significant figures in the volume. I need 4 significant figures. These leading zeros are not significant. So our non-zero digits are 1, 2, 3. This is significant. I look next door, and I'm going to end up dropping that 3 because I'm not going to round. So my molarity would be reported 0.06997 capital M molar. Now for this particular problem, I actually expanded it slightly. And what I want to do now is find the molarity of the calcium cations in the above solution as well as the hydroxide anions. And that is using the stoichiometry of the chemical formula. So there is 1 calcium cation there is 1 mole of calcium cations for every 1 mole of calcium hydroxide. Therefore, the concentration of calcium cations, and we show concentration with molarity, we show it with square brackets. So the concentration of calcium cations is going to be equal to the concentration of our calcium hydroxide, which is 0.06997 moles, or molar. What is the molarity of the hydroxide anions? Well, this time we have a small calculation to do. So the concentration of our calcium hydroxide is 0.06997, and that's moles, and I'm going to write this out on purpose, of calcium hydroxide per 1 liter. Now, in 1 mole of calcium hydroxide, there are 2 moles of hydroxide ions, and I find that right here with my subscript. So I multiply this value by 2 in order to get the concentration of the hydroxide. 0.1399 is what I get here, capital M molar. And that is the concentration of the hydroxide ions in this solution. Number 4, we're going to find the molarity of 2.76 kilograms of a copper sulfate pentahydrate. Now, I chose this one on purpose because you are using this in your lab for this module, or the next module, depending on which course you're taking. So we're going to start with 2.76 kilograms of this copper pentahydrate, copper sulfate pentahydrate. That's how that is named, and it's a copper 2. Now I'm going to convert these kilograms into grams because our molar mass is in grams. Now, how are we going to calculate this formula mass? Well, just like you would for any other compound. So we have copper, which is 63.55, and sulfur, which I may have written up above, but I may not. Sulfur is 32.06. Oxygen, I'm just going to use 16. And hydrogen is 1.01. So that gives us all of our atoms. So I'm going to start with the copper and add 63.55 plus 32.06 because I have one of each of those. Then I'm going to count all of the oxygens and just do this at once. So I have 4 here, and then I distribute this 5. So I have 5 oxygens here. So I actually have 9 times 16 when I'm adding this formula mass. And then for the hydrogen, I have 10 hydrogens. So I'm going to multiply 1.01 times 10, add that all together, and I get a formula mass for copper 2 sulfate pentahydrate of 249.71 grams per mole. Now the point is we need to find the moles so that we can calculate the molarity. So I'm going to take 2.76 kilograms, multiply it by 1,000 to get grams, and then divide that by 249.71, the molar mass. And I get 11.05, and I have one more sig fig on purpose, 11.05 moles of my copper sulfate pentahydrate. And now I can calculate the concentration. Now, do leave these numbers in your calculator and only round at the end. So I'm going to leave this number in my calculator and divide it by 1.45 capital L liters. Remember, when you're finding molarity, you need to use liters. And I get 7.62 capital M molar, and that is the concentration of copper sulfate pentahydrate. 3 sig figs in my question leads to 3 sig figs for my molarity. So what is the mass of the solute in half a liter of a 0.3 molar glucose solution used for IV injection? Well, we're going to start with the volume here. So 0.500 liters of solution, and then we're going to use molarity as a conversion factor because what that says is there are 0.30 moles of glucose for every 1 liter of glucose. Now, it specifically asked for mass. Mass is not moles. Mass is going to be grams. So I need to find this formula mass. I'm going to use carbon is 12.01, hydrogen is 1.01, and I'm going to use oxygen at 16.00. So I just add all of those up. Make sure I multiply in the right places. So because what I mean by that is we're going to take 6 carbons, so 6 times 12.01, add that to 12 times 1.01, and then add that to 6 times 16. And I get a formula mass or a molar mass of 180.18 grams per mole. So now I multiply that 180.18 times 0.3 times 0.5, and because our dimensional analysis worked here, 27.027 is what my calculator gives me. But I need to check for significant digits. I have 3 significant digits in my volume, but only 2 significant digits in my molarity. So I can only report 2 significant digits, 27 grams. Now we're going to calculate the number of moles and the mass of the solute in each of these solutions. So here we have 2 liters of an 18.5 molar sulfuric acid solution. So we're going to calculate the number of moles first. So we start with our volume, 2.00 liters of solution, and we're going to multiply that by the concentration, 18.5 moles of H2SO4 for every 1 liter. So 2 times 18.5 will give us the moles, and we have 37.0 moles of H2SO4. So that's the answer to the first question. We have moles first and then mass. So now we need to find the molar mass. So hydrogen is still 1.01. Sulfur, I'm using 32.06. And oxygen is 16.00. So to find the molar mass, 2 times my hydrogen plus sulfur plus 16 times 4. And I get a molar mass of 98.08 grams of H2SO4 for every 1 mole. So I multiply that 98.08 by the 37 moles and get 3,628.96 grams of sulfuric acid. And now I need to look for my sig figs. I had 3 significant digits in the volume, 3 significant digits in the molarity, so I can only end with 3 significant digits. And it would be easier, it would just be more convenient if I could report this as 3.63 kilograms. Kilogram is okay to be reporting a mass. Make sure if you have a blank instead of a text box on a quiz, make sure you pay attention to what units are expected. 3,630 would also be 3 significant digits if it was grams. Number 2, again, we're going to start with the volume. I'm going to convert that into liters and multiply it by the molarity. So that's moles of NaCN per 1 liter of solution. So I multiply 3.8 times 10 to the negative 5 times 0.1 and get 3.8 times 10 to the negative 6 moles of NaCN. The second part of the question is what is the mass? So I need the molar mass or the formula mass. So I'm going to use sodium is 22.99, carbon is 12.01, and nitrogen is 14.01. And I just add all of those together. 49.01. Multiply that times the number of moles and get 1.86 times 10 to the negative 4. Now the units for that are grams. And that is sodium cyanide. Oh, and I didn't significant figure that. So the volume has 4 significant digits, but the molarity here only has 2. So we would round that 1.9 times 10 to the negative 4. That would be correct significant figures for that question. What is the molarity of KMnO4 in a solution of 0.0908 grams of KMnO4? Well, again, 99% of the time you see grams in here. You're going to need to convert it into moles. So we take those grams and find the formula mass. Now this time, the formula mass for KMNO4, number 4, is 158.04 per mole. So we calculate the moles. I get 5.74 times 10 to the negative 4 moles, KMNO4. Then divide those moles by the volume in liters and get 1.15 times 10 to the negative 3 capital M molarity of KMNO4. Number 5, what's the molarity of HCl? If 35.23 milliliters of a solution of HCl contain 0.3366 grams of HCl, well, again, with the mass, we have 0.3366 grams of HCl. We need to use the formula mass. So 1 mole of HCl is 36.46 grams of HCl. So I get 9.232, and I'm going to leave this in my calculator, times 10 to the negative 3 moles of HCl. Now I need to divide that by the volume. Now I need to convert this volume into liters. So it's going to be 0.03523 capital L liters, 3523, and I get a concentration of 262. I actually get a 0.5. Now I have 4 sig figs here and 4 sig figs here. Because I get a 0.5, I'm going to round that up to 1. Now you may find, depending on which major you're in, so the rounding rules. Because there's a 5 here and 0 is considered an even number. In many instances, the rounding rules would say you just drop it because you want an even number. However, the way I was taught in Old Habits Die Hard is if it's a 5 or greater, you round up regardless of whether this is even or odd. I will have that flexibility built into my classroom because I don't want to teach you the chemistry way if the way that your major rounds is different. So round the way that your major teaches you, and I will adjust. Number 6, what volume of 1 molar FeNO33 solution, so that's iron 3 nitrate, can be diluted to prepare 1 liter of solution with a concentration of 0.25 molar? Well, we need the dilution equation, which is M1V1 equals M2V2. Now, as long as you keep your 1s and 2s together, you should be able to work this out. So what volume tells me that this volume is unknown of my 1.00 M is equal to, and then this volume goes with my 1.00 liter, and that 1 liter of solution has a concentration of 0.250 capital M molar. So then you solve for V, and that V is going to be 0.250 liters. Number 7, one that's slightly more difficult. If this volume, so I'm going to call this volume 1 of this molarity, I'm going to call this molarity 1, is diluted to a concentration of M2, then what is the volume? Well, now I just plug in my values to this equation. This is the dilution equation. So M1 is 0.3556 volume, and that's capital M molarity. The volume is 0.1718 liters, and that's going to be equal to 0.1222 capital M molarity times volume 2 that I don't know. So first I multiply my 0.3556 by 0.1718, and I get a value of 0.0610928, and I'm giving you all of those digits on purpose so that you can double check your calculating. But that is not correct significant digits. Now I divide both sides by 0.1222, and I get a V, a volume, in liters let's see, I'm looking for 4 significant figures, I think, but I get 0.4999, and then I have a 3. So that 3 would get dropped. We're not rounding up, and the units here are capital L liters.